Okay, good evening. So far as the syllabus is concerned, we'll start mass spectrometry. So, theory and instrumentation, unit mass and molecular ions, important terms like singly doubly multiple charged ions, metastable peaks, base peak. And what is the difference between metastable and base peak? Are they same or different? Then isotopic mass peaks, relative intensity, recognition of M plus ion peak. That means the mother ion. Ionization method. What are the different ionization methods? So then the general fragmentation rule. Last we'll discuss the structural elucidation of compounds containing IR, NMR and mass spectra. Examples of structural elucidation. Okay. So the basic principle in mass spectrometry is the most accurate method for determining the molecular mass of the compound and its elemental composition. In this technique, the molecules are bombarded with a beam of energetic electrons. The molecules are ionized and then broken into many fragments, and obviously, some of which are positive ions. And each kind of ion, because they will split into different fragments giving positive charge ions, and each ions will have different mass, or in other words, they will have different mass to charge ratio, m by e ratio. And for most ions the charge is 1, so one electron will be removed, so m by e ratio is simply the molecular mass of the ion. One example is given here. Let the neopentane, so when it is bombarded with high energetic electron, so one electron will be released from this compound, so we'll get the molecular ion. So the molecular ion is C5H12 plus, where M by E ratio is 72, just the molecular mass. Again, this molecular ion will go into fragmentation. So when it will fragment, there will be chain cleavage. So it may cleave from here, giving rise to C4H9, or two methyl groups can be released, giving with one hydrogen, so C3H5, C2H5. So like that, different fragmentation will be there, and we can analyze because they will have just one positive charge. So M by E ratio will be equal to the molecular, the mass of the ion. Sorry. So the molecular ion here, that is C5H12, it is called the parent ion, which is generally designated by M plus, and others are daughter, that means fragmented ions. And so the fragment ions or daughter ions are analyzed in such a way that a signal is obtained for each value of m by e, and which will have the maximum intensity that will designate it as the base peak. Okay, so the intensity of each signal is represented in the relative abundance of the ion. The largest peak in the structure is called the base peak, and its intensity is taken as 100 arbitrarily. So with respect to the intensity of the base peak, others relative intensity we have to find out, and where it will get the peak, that will give you the molecular mass. A single mass spectrum is equivalent to dozen of physical. So therefore, each molecule in organic chemistry will have its own identical mass spectroscopy. So we can use the mass spectra to prove the identity of two compounds or to establish the structure of a new compound. So it is also used to establish the structure of a new compound in several ways, like it can give the exact molecular mass, it can give a molecular formula, or it can reveal the presence of certain structural units in a molecule. So col- in with the help of NMR and IR and also mass, we can elucidate the structure of a new organic compound or new compound. Now moving towards the theory. So as we know, when it is bombarded with electron, high energetic electron, one electron will be removed, so the parent ion or the mother ion will be formed with M plus. The M by E value of the parent ion is equal to the molecular mass of the compound. So in a few cases, the parent ion peak may be the base peak and can be easily recognized, but in most of the cases, the parent ion peak and the base peak are different. So in that case, we have to judge which is the parent ion peak and which is the base peak. So the parent ion peak may be have very small abundance, but which will have the highest abundance, that will be in the scale. We have to choose it as 100%. So that will be our base peak. But the parent peak, it may be higher, having higher M by E ratio. Okay, so many elements occur naturally as isotopes. Out of these, the lightest one greatly predominates. The mass spectrometer is designed to perform three basic functions, like how we'll have to analyze. So to vaporize the compound, of having volatility, we have to vaporize the compound, then to produce ions from the neutral compound in the vapor phase by bombardment of electrons, and to separate the ions according to their mass over charge ratio and to record them. The plot of M by A value taken along abscissa and their relative intensities are along the ordinate. It's called the mass spectrum. So this is the how fragmentation occurs. Neutral particle produced in the process of fragmentation cannot be detected. So this is the peak as given by neopentane. You can see here the molecular ion peak is 72, but it is not the base peak. Base peak is C4S19, having M by E ratio 57, is the having 100% abundance. Others, the relative abundance is given here 27, 29, 41, like this. This is not 29, this will be 39. Mistake. Let me check here. 17, I think, yes. 27, 29. Molecular mass is
Pardon,
of 38 and 50. Yes.
pardon, sir. Sir, here
Yes.
as we were explaining here, this one that 72
Mm-hmm.
we are getting this neopentane. So whenever we
Mm-hmm.
analyze, it will be means if it is neopentane at that 72 only, always this best peak will come, or is there any something means
This
variability?
is the parent. No, no, no. This is the parent peak.
Acha,
Parent
acha.
peak is when only one electron will be removed, will get the molecular ion. So that is the parent peak. But base peak is different. Base
Okay.
peak, which will have relative abundance of 100%. The largest
So
peak will be the base peak.
okay, so
Yes.
here what is showing that M by E 57, that is the peak over here we are considering. If it is
This
the
is the
spectrum.
this is the base peak.
Okay, sir.
57 m by so this is the base peak, but parent peak is 72. See, what is the difference? Which will have the highest abundance? That is your base peak, and which is the having
Okay.
highest m by a value? That is the
Hmm.
parent peak.
Okay.
because when only one electron will be removed from the molecule, you will get the parent ion.
Okay.
But after fragmentation, which will have relatively high abundance, that is your base peak.
And probability will be based on that high abundance, that probably this molecule is only present whatever the sample being injected. Is it so?
No, no. This is the highest peak, means its relative abundance means 100, means in the probability for
Okay.
formation of this fragment is maximum.
Okay. Okay.
That means when this bond will cleave, one CC bond will be cleaved, you will get C4H9. Yes or no?
Yes, sir.
If it will
Sir,
cleave heterolytically, CH3 minus will be there and you will get C4H9 plus.
yeah, right.
So relative abundance of this ion, this one will be maximum.
Sir,
Then this
basically
will be
my
the
what.
base peak.
Okay, sir. So what I wish to ask here, that if this
Uh,
spectrum is given to me as an
uh,
unknown compound, so which one
yes.
should I choose that most means the probability of being this molecule in this sample is the most. So which peak I should choose over here? This best
Okay.
probable one
Okay.
or
Okay.
parent of? Okay.
See how, what is the other options that if you discuss, then we'll get the answer. If it is neopentane, isopentane, n-pentane, whatever may be, okay,
Okay.
all the isomers of pentane
Yeah.
will have the same molecular formula, same molecular mass. Yes or no?
Yes. Yes. Right.
So the mother peak for all the isomers of pentane will be same 72.
Yes.
Yes or no?
Agree, sir. Yes.
But where will be the difference? Here is only. Here will be the difference in the base peak and other the daughter peaks. Because
Okay.
if it is neopentane, then it will split. When this will be fragmented, you will get C4H9, one methyl group will be removed,
Yes.
and here you will get C3H5, C2H5. How will you get C3H5? C3H6, one hydrogen is also removed, so you will get C3H5, C2H5.
If
Okay,
propane and
and
ethyl like that, then E3 and C2 it is coming.
yes,
Propyl and
but in case of normal pentane, you will
yes,
not get this fragment C4H9.
yes.
Because how will you get? You only when one methyl group will be removed, you will get C4H9. But in case of normal pentane, N-pentane,
Hmm. So here basically
so
for neopentane, this is coming out owing to the steric hindrance. Is it so or something else?
it's not like that. No steric hindrance, nothing will be there because this is, you have to vaporize the compound. If
Okay.
it is in liquid solid phase, you have to vaporize. You have to
Hmm.
bombard it with high energetic electron. Then you have to
Hmm.
produce the ion. You have to analyze according to their
Okay.
atomic mass. Sorry, molecular mass. M by E ratio, they will be separated and you have to analyze. So what are the daughter peaks or molecular mass of the peaks? Then you have to analyze what will be the compound. But it will give only the molecular mass of the different fragments.
Okay.
Okay, and you
Yes,
can
sir.
analyze the isomer also. But to predict the exact structure of the compound, you have to take the help of NMR and IR also.
So basically
Combiningly,
from
NMR,
this one,
IR,
pardon
you
sir.
will get the molecule. You will get the molecular mass.
So from this spectrum, I am getting the information here one pentane is there, but whether which isomer of pentane that I cannot decide from here.
No,
Okay.
collectively you have to decide taking the help of NMR and IR
Okay.
is not required. NMR and this one.
So that means
Okay.
this
Will
72, this, sorry, sir. Okay.
72 is all isomers of pentane will give the peak this peak, but this
Okay.
fragment peak will be different. This will be different,
Okay.
but 72 will be
Based
same.
on
Will be same.
item. Okay.
Yeah.
Thank you.
Then it. Thank- Welcome. So regarding the instrumentation, so as we have discussed the basic principle, we have to uh, vaporize the compound first. The compound will be in vapor phase. Then you have to ionize the compound. Then we have to detect, basing upon their M by E ratio. So three basic things will be there. So one is the ion ion source. The first and important step in obtaining the mass spectrum is to ionize the sample under examination. The minimum energy required to ionize an atom or a molecule is called ionization potential or ionization enthalpy or potential. The common technique used for the production of ions in mass spectrophotometer or mass spectrometer is by the bombardment of electrons. So gas samples enters here, then this is the filament current which will ionize the gas. Then ions are accelerated. Why acceleration is required? Because the acceleration, then there will be change in path. The force which will be exerted when the particle will be accelerated, there will be change or electric field will be generated. You know this one basic principle. If any charged particle is accelerated in an external magnetic field, then it will lose energy. Then it will change its path. So when path will be changed, and that changing in path depends upon the mass. So as m by e ratio for different fragments is different, so their path or diversion will be different. Then we have to separate those ions and we will detect them. So that is the thing. So ions accelerate towards the charge select, this is charge, and magnetic field deflects the lightest ion most and heaviest ion least. Then ions are separated by mass exposed film or they are detected. So vapors are coming again. This is the schematic diagram. Uh, and source is there, so repeller potential, then acceleration potential, then to analyzer. Okay, so the bombarding electrons are produced from an electrically heated tungsten filament. A few milligram of substance is produced as a vapor in the source at an operating pressure of 10 to the power minus 6 millimeter of mercury. The vapor is allowed to pass through a slit into the ion chamber. Here it is bombarded by a stream of electrons produced from the tungsten filament. The bombarding electron have energy about 70 electron volt, and due to this bombardment, the molecule generally lose one electron to form the parent ion radical. So this is the phenomenon, the movement of electrons. So let A be the molecule. So AB parent ion radical is formed by releasing one electron. When two electrons will be released, we'll get the AB plus. Okay. So this is the most probable, that is the parent ion. Then the least probable N plus formation is very difficult, and AB, then there will be fragmentation. The AB plus may be converted to A plus B minus, or it will be converted to A plus plus B plus 2 electron will be released, or by releasing it will also produce AB minus by acceptance of electron. So these things will not be detected, the negative ions, electron capture, which is least probable. So negative ions cannot be detected, only positive. So the energy required for removing one electron from the neutral parent molecule is usually 10 electron volt. With this much energy, no ions are formed, so no fragmentation a parent ion takes place. But if the energy of the bombarding electron is around 70 electron volt, then additional energy is consumed in the fragments in fragmenting the parent ion. This results in the formation of fragment ions or the daughter ions. So the positive ion, whether even electron or odd electron species, is detected in the mass spectrometer, whereas the neutral molecules or the radicals are left undetected. Then moving to the second part, that the mass analyzer, the positive charge ions, either the parent ion or fragment ions produced in the ion chamber, are accelerated by applying an acceleration potential. These ions then enter the mass analyzer. Here the fragments are differentiated according to their mass or M by E ratio. The positive ions are directed towards through a slit. Then repeller potential is applied between A and B. So these ions, the ions are accelerated by applying an acceleration potential of the order 8 kilovolt through the slit C. Acceleration potential is applied between the plates A and B. The positive ions are traveled through whole analyzer portion and mass spectrometer with high velocity and are separated according to the M by E ratio. So now the theory, if you see, we know if we are having a magnetic field of H, so this is here, the figure is there. You have the magnetic field is a circular path where the ion will travel. Accelerated ions, then with the semicircular field it will be accelerated, then there will be separated. So if you see the kinetic energy of the movable electron, if it is moving with velocity v, then half mv square, which is equal to ev, where e is the charge of electron and v is the potential difference of voltage applied. So half mv square equal to ev. And now if the magnetic field of H is applied here, where the ion will experience a force which will be equal to H into E into V, magnetic field. So magnetic force H E V, and acceleration will be V square by R. R is the radius of the circular path. So H E V equal to mv square by R. Or if you square, then it will be S square E square V square equal to m square V square, sorry, V to the power 4 by R square. And we know here half mv square equal to ev. So mv square will be equal to twice ev. So putting this m square v square here, mv square equal to twice ev. So finally we will get h square e square equal to twice mev by r square. One e will cancel, so h square e equal to 2 mv by r square, or m by e, mass to charge ratio, m by e equal to h square r square by twice v. So here if you increase, so the m by e, it will be detected by changing the potential or the magnetic field. So from this equation, it is clear that for a given magnetic field strength, the accelerating voltage, the ions of m by e value will follow a circular path of radius r. Now the ions of various m by e values reach the collector, amplified and recorded. The mass spectrum can be obtained either way, because we have to detect all the ions with complete m by total m by e value. So we have to change, either we have to change the field strength keeping the potential difference constant, or we have to change the potential difference keeping the magnetic field strength constant. So this one. So when magnetic field is varied, the method is called magnetic scanning, and when electric field is potential is varied, it is called electric scanning, electric voltage scanning. So these things, another instrumentation. Then we will move to the ion detector. So the ion which are separated by the analyzer are detected and measured electrically or photographically. The ions pass through the collecting slit one after the other and fall on the detector. The spectrum is scanned by going up the scale from higher m by e ratio to, sorry, lower m by e ratio to higher m by e ratio. The ion current are amplified using a direct current amplifier. The spectrum is recorded by using a fast scanning oscillograph. This type of recording, 3 to 5 records of the same peak are made with galvanometers having different sensitivities. On the mass spectrum, so as you know, we have to record the mass spectrum is nothing, it is the a plot between the relative abundance to m by e ratio. So it is a record of masses and the relative abundance of the molecular ion and the positively charged fragments formed from it by electron bombardment. The m by e ratio are taken along the abscissa while the relative abundance are taken in the ordinate. Okay, the base peak is the highest peak or the most intense peak in the spectrum. But parent ion peak is the peak of highest m by e ratio. The relative abundance of ion means the percentage of the total ion current. Then the molecular ion or parent ion, the electron bombardment with energy only 10 to 15 electron volt usually remove one electron from the molecule of the organic compound in the vapor phase. It results in the formation of molecular ion. The highest occupied orbital of aromatic system and non-bonding electron orbitals of oxygen and nitrogen atoms readily lose one electron. An electron from double bond, that means 2 pi electrons, or triple bond 4 pi electrons is usually lost. In alkane, the ionization of CC sigma bond is easier than CH bond. Is it clear? The ionization of CC sigma bond is
Yes,
easier
sir.
than the CH bond. So that's why the base peak, when you are getting the relative abundance of the base peak is maximum, means when in neopentane you have seen where it is. Relative abundance of this peak is maximum. Why? It is easy to cleave one carbon-carbon bond rather than the CH bond. So when a CH bond will cleave, you will get the parent ion. But its relative abundance, you can see here, it is only 10%, you can say.
Sir,
The
pardon, sir.
cleavage of one
Another,
carbon-carbon.
sir.
Hmm.
Another
Yes.
doubt is coming. That is,
Hmm.
as you said, that this relative abundance of this peak we can see. So that means whenever if it is neopentane, if it is injected, the probability of getting this similar pattern always will be obtained, or it may vary also.
No,
If
no,
it
it
is
will not
neopentane,
vary.
it is
It is
similar pattern
neopentane, it
will
will
get
get the same, not similar, the same pattern.
same. Okay. And
It
sir,
will, you will
what
get
is
the
the
same.
Okay, that means
Yes.
first there is one small, then bigger, then gradually like four lines are coming. So similar that four pattern with the similar ions, you will get it.
You will get
Okay,
the same pattern, not similar.
okay,
Okay.
sir, same.
Because this is a
Thank you.
fingerprint. Yeah. Same pattern.
Okay, sir.
Okay.
Sir, another doubt is there. May I ask, sir? Sir, how
Okay. Ask.
the detector is detecting that it is neopentane or pentane? Means what is the standard is used? Like
It,
detector, as you said, what is the
it
standard
will
is used
not,
to
it will
calibrate?
not, okay. Okay. It will not detect whether it is neopentane, isopentane, or whatever may be. It will detect what is its mass only. What is the mass of that ion? It will detect that much.
Okay, so what I mean to wanted to ask is, sir, means that
Hmm.
means something we are feeding the knowledge to the detector that if this is coming, then it has to take like this. So, what is that kind of standard or some what is called some chemical we are feeding over there so that the detector will calibrate it and accordingly it will understand that this much
De-
carbon
de-
is
de-
coming. So,
Definitely, we have to calibrate. The instrument is calibrated. The same mass you need to. What is the how to calibrate the atomic mass? What
okay.
is how to calibrate the atomic mass of hydrogen? As it is coming for one, for example, 1.008.
So, what
How it
do
is
they use
calibrated?
actually? This one means uh, if
Use
they
means
wish means like like for means what I mean to say, if I need to see the pH of a sample, so I have seen the space, even this water filter person or whoever is coming, they will have some solution. So first they will calibrate if this is coming pH this, if this is coming pH this, then based on that I should
okay,
define
okay.
this in order. So, so
I
what
got the point.
should be given the detector so that what exactly they are doing? So the detector is detecting mass is this.
That's why I asked you how you are calibrating or upon which standard you are calibrating the atomic mass. If you know that one, then the same thing is in the same way it is calibrated. What is the atomic? How we are calibrating? How we are telling that atomic mass of hydrogen is 1.008? Why not it is 2.00 something?
So what
You
kind of
have
standard do
standardized.
they use? Acha.
You have standardized the atomic mass with respect to the 1/12 of carbon 12 isotope.
Okay, sir.
Yes or no?
Yes.
So the same way we have given that feed to the detector that if it is carbon, this mass is coming, then take it as carbon.
Okay.
Okay, it is programmed in such way, in that way only. If this one you are detecting this mass, because first let we have feed there only the carbon vapor.
Okay.
Okay, carbon
Yes,
vapor
sir. Hmm.
or hydrogen vapor, knowingly known element, pure known element. Let hydrogen vapor. It will be ionized to H plus. So in that way, the machine is calibrated. Which ion will be detected? That will have the M by A ratio equal to 1 if it is hydrogen. So with the
Okay.
same element, known element, the vapor of known element, first we have to calibrate the instrument. It
So
is
that means if
calibrated.
it
You
is
know,
neopentan, we have to give neopentan sample only, that pure standard only.
no. You are not getting my point. You will not you don't have to calibrate the instrument. The
Okay.
instrument is already calibrated by the company.
Okay.
Okay, how it is calibrated, I am telling. First, or if you want to calibrate, you can calibrate with not neopentane. With not
Okay.
neopentane, you have to calibrate an instrument with simple element: hydrogen, carbon vapor,
Okay.
nitrogen, oxygen. Okay,
Acha,
pure element.
elemental state, pure elemental state, it will be fed over there.
You have to calibrate.
Okay.
Inject hydrogen vapor. You inject
Hmm.
hydrogen vapor, ionize it, detect it. What you will detect if the machine is telling that a 2 mi ratio 2, then you will calibrate it to 1 because it is only
Yes.
hydrogen. So mi ratio should be 1. So you change the knob. You no need to change. It is calibrated. I am telling how to calibrate.
Yes.
You don't have to calibrate.
Okay.
Okay, like pH, like the pH you are adjusting, known pH solution, you are dipping
Hmm.
the electrode with
Hmm.
a known pH solution, then you are changing the knob.
Yes.
Yes or no? 4,
Yes.
4, 9, 9, 7, like this you are changing, then that is calibration. Then you are taking the pH of unknown sample.
Oh,
So here calibration is already done. How it is done? By injecting the pure element. vapor of pure element like hydrogen, carbon, oxygen. Because carbon and hydrogen, they are the standard. Carbon
Carbon
12
vapor, that will be
isotope.
huge temperature. Carbon
Pardon?
vapor. Carbon vapor means it will be, I think, huge temperature.
It will be
Temperature will be extremely high, I believe. This one.
whatever is the temperature, because the ion source is there now, you have to ionize.
Yes, sir.
It is not only you have to simply give the organic compound. Extreme temperature means if you pass electric discharge,
Yes, sir. Got it.
then you can get also carbon vapor. So anyway, so you'll get the molecular ion or parent ion. These things we have already. Yes. So the mass of the parent ion gives the molecular mass of the sample. The mass of the parent ion gives the molecular mass of the sample. In the mass spectrum, it is important to locate the molecular ion, which is at the highest or high mass region of the spectrum. Already we have seen that one. Then the stability of the parent or molecular ion decides its relative abundance. As I told in case of neopentane, the stability of parent ion is very less. So that's why its relative abundance is less. Because breaking of a carbon-carbon bond is easier than a carbon-hydrogen bond. So if there will be carbon-hydrogen bond breaking takes place, but by rearrangement, we'll see after this. By rearrangement, there will be a breakage of carbon-carbon bond. So that's why we will get the base peak or base ion. So the peak intensity of the molecular ion differ from one compound to another. In some cases, the parent ion peak is not formed, which means that the rate of decomposition of the parent ion is too high for its detection. As the parent ion is formed, then it will break to give the base peak. So it is important to note that the rate of decomposition of the molecular ion increases with molecular size in the homologous series. Larger molecular ion provides more possible reaction pathway for detection. As you can see, the benzene, this is the parent ion. In case of alcohol, this is the parent ion. Same thing in case of alkene. See, only one electron will remove, so this is the parent ion. One exercise is here. Predict the relative abundance of the parent ion in case of propane and neopentane. The relative abundance of propane molecular ion is more. The abundance of molecular ion peak can be increased with respect to abundance of fragment ion by running the spectrum at low ionization potential. That means I am bombarding low energy electron. So when you are bombarded with low energy electron, then only the molecular peak, the molecular ion peak, the abundance can be increased, because with low energy electron only one electron will be released. If you bombard with
Pardon.
high energetic electron, yes,
Sir, here we can control this energy of the electron by controlling the potential difference.
yes, because
Okay.
EV charge of electron cannot
Yes, sir.
be changed. If you change the potential difference, the energy of the kinetic energy of electron will increase
Yes,
or
sir.
decrease.
Yes, sir.
So potential you have to change. So now some important features of the parent ion peak, which are as follows. The molecular ion peak in aromatic compounds is relatively much intense due to presence of pi electron. If pi electron system will be there, then you will get the molecular ion peak having high intensity. Conjugated olefins, they also show more intense molecular ion peak because it is conjugated. Conjugated means nearly so more delocalized as compared to corresponding non-conjugated olefins with the same number of unsaturation. Conjugated olefins are more stable than corresponding non-conjugated olefins. So you'll get the more intense molecular ion peak. Unsaturated compounds give more intense peak as compared to saturated or cyclic because by presence of pi electron. The relative abundance of saturated hydrocarbon is more than the corresponding branch chain compounds with the same number of carbon atoms. For example, molecular ion of N-pentane is more intense than that of neopentane. To follow, the relative abundance of saturated hydrocarbon is more than corresponding branch chain compound with the same number of carbon atoms. In case of saturated hydrocarbon, if it is straight chain, if it is straight chain, then the relative abundance of the molecular ion will be more when it is branched. That's why in case of N-pentane, you will get the molecular ion peak which will be more intense than neopentane. Neopentane is more branched, that's why molecular ion peak is less intense. The substituent groups like hydroxyl, methoxyl, amine, they will have lone pair of electrons. Therefore, they will have lower ionization potential, which will increase the relative abundance in case of aromatic compounds. Also, in groups like nitro and cyano, which increase the ionization potential, decrease the relative abundance of the aromatic compound. Absence of molecular ion peak in mass spectrum means that the compound under examination is highly branched or tertiary alcohols. If there will be absence of molecular peak, then the compound is highly branched, or in case of tertiary alcohol, also will not get the molecular peak. Primary and secondary alcohol give very small molecular ion peaks. In case of chlorobromo compounds, isotopics are also formed along with molecular ion peaks. In case of bromo compound, you can see M and M plus 2 peaks are formed in the intensity ratio 1 is to 1. In chloro compounds, M plus and M plus 2 peaks are also formed in the intensity ratio 1 is to 3. So the isotopic means chlorine 35, 36, 37. Three isotopes are there. So M plus 2 means if it is 35, this is 37 isotope. So you will get in the ratio 1 is to 3, in this case 1 is to 1. Bromo, in case of bromo. So now how to determine the molecular formula? See, the mass spectrum of ethyl bromide is given here. As I told, in case of bromine, you'll get the same intensity for M plus and M plus 2, the isotopics 108 and 110. And along with that one, you see 79 and 81, you are getting, and 29, you are getting the base peak at 29. So you can analyze this one. The mass spectrum is a plot representing the M by E value of the various ions, parent as well as fragment ions against their corresponding relative abundance. The peak of the extreme right gives you that means the particle of highest mass corresponding to molecular mass of the original molecule. In case of straight chain hydrocarbon, the abundance of parent ion peak is fair, as it also gives M plus 1 peak, which is 9.9% abundance compared to the parent peak. M plus 1 in this case, the isotopic, maybe the hydrogen isotope. But consider that a compound forms peak of M by value of 100, 85, 71, 57, and 43, which have 100%. Clearly, it is a straight chain alkane because fragment peaks are formed 14 units apart, you can see. Nearly 14 units. So that means CH2, methylene group, carbon 12 plus H2 means 2. So 14 apart means the fragments are only one methyl group, CH2 group fragment occurs. So that's why it is a hydrocarbon. In case of straight chain hydrocarbon, a peak due to C3H7, okay, is most abundant, so that is the base peak. Thus, a molecular formula of the compound can be obtained. In case of organic compounds, give fragment as well as parent peak in pairs which are 2 units apart. Then, if the pair of peaks are intensity by 1 is to 3, as already discussed, then it is a chloro compound. If it is 1 is to 1, then it is a bromo compound. So, you can see here that 1 is to 1, so it is a bromo compound. So, you can see here. So, if you want to discuss the spectra, you can see the pair of peaks of equal intensity. Which one? 79, 81 or 180 and 110. So that means it is a bromo compound. The isotopes of bromine, which are bromine 79 and bromine 81. The pair on the extreme right corresponds to M plus and M plus 2, that is 108 and 110. The spectrum corresponds to the molecular formula. If it is 108 or 110, it should be C2H5Br. Bromine is let bromine is 79, H5 means 5, so 79 plus 5 84, and carbon 2 carbons means 24. So 84 24 108, and M plus 2 will be 110. So the spectrum is C2H5Br. So like this we have to analyze, and in some cases also there will be McLafferty rearrangement and peaks. So what is that McLafferty rearrangement? So, so it gives an important clue for determination of molecular formula of the compound. For example, all straight aldehydes containing gamma hydrogen atom form a base peak at M by E 44. That is McLafferty rearrangement ion peaks. You can go through this one. You can see here alpha, beta, gamma. If there will be gamma hydrogen, so it involves the migration of gamma hydrogen atom followed by a cleavage of beta bond. So beta bond means here, this one there will be cleavage. Okay, so CH2 double bond will be formed. So enol will be formed, enolate. So first you see there will be cyclation rearrangement. As already I told, one hydrogen will be migrated. You'll get the, in some cases you'll get the fragment. So it involves the migration of gamma hydrogen atom followed by cleavage of beta bond. The rearrangement leads to elimination of neutral molecules from aldehydes, ketones, amines, unsaturated compounds, unsubstituted aromatic compounds, etc. The rearrangement proceeds through a sterically hindered six-member transition state, then formation of the enol form. So that means McLafferty rearranged ions. See the transition state. So we have butanol, which is having a gamma hydrogen atom. So the McLafferty rearrangement ion formed in this case will be the enol CH2 CHOH enolate is rearranged product plus this will be your alkene. In case of butanol, it is ethylene, or in some cases you get the alkene. Similarly, a large number of organic compounds, ketones, amines, alcohols, esters, acids, which contain gamma hydrogen atom, they undergo this rearrangement. Thus, the molecular formula of the unknown compound can be determined from the various fragments ions and also the pattern of the mass spectrum. So you can see here pentene. Pentene undergoes McLafferty rearrangement. One removal of this is alpha, beta, gamma hydrogen atom, producing their cleavage. So ethylene and double bond. So propene ion. So this will be detected. Similarly, in this case also you will get styrene as the neutral molecule and enol, this propanol as the ion, McLafferty rearranged ion having molecular M by E ratio 58. So there are some other examples. You can go through this one. Metastable ions or peaks. Metastable peaks can be easily determined in the mass spectrum. Some important characteristics of the peak are they don't necessarily occur at the integral of m by e value because these peaks are metastable. They will be converted to the stable fragment. So in between some m by e value will get not at the integral value. These are much broader than the normal peaks and these are relatively low abundance. So example, if you see the metastable, the position of metastable peak, see here at 94.8 in case of this one. Okay, then we'll move to the nitrogen. Okay, nitrogen rule. Many signals peak can be ruled out as possible molecular ion simply on the ground of reasonable structural requirement. The nitrogen rule is often helpful. It states that a molecule or even numbered molecular mass must contain no nitrogen atom or an even number of nitrogen atoms. An odd number molecular mass require an odd number of nitrogen atoms. If the molecular mass ion is even, so it may contain no nitrogen, it may not contain any nitrogen or it may contain two nitrogens. And if the molecular mass is odd, then there must be one nitrogen atom. That is nitrogen rule. So this rule holds for all compounds containing carbon, hydrogen, oxygen, nitrogen. Okay? Because you see, always there will be even number of hydrogen in comparison to carbon. Molecular formula alkane CnH2n plus 2 given alkene CnH2n alkyne CnH2n minus 2. So even number of hydrogen and carbon, see carbon atomic mass is 12. So even hydrogen atomic mass is 1, but always there will be even number of hydrogen in organic compound. So as a whole, atomic mass will be even. Sorry, molecular mass will be even. But if oxygen will be present, then also it will be even because with removal of two hydrogen, one oxygen will be produced. One oxygen will be inserted or substituted. So when one oxygen will be present, two hydrogen will be removed. So again molecular mass will be even. If chlorine will be attached, molecular mass of chlorine is odd, 35.5 or 35 we're telling. So when one hydrogen will be released, one chlorine will be there. So odd, so ultimately it will be. So presence of nitrogen is the only problem. Because nitrogen when it will be present, nitrogen atomic mass is odd, sorry, even, but when one hydrogen will be removed, one nitrogen will be there. Therefore, it will be having the problem. So therefore, if atomic mass or molecular mass of the molecular ion, the molecular mass it will contain, so if it will be even, then it may contain no hydrogen or it may not contain any hydrogen or it may contain even number of nitrogen. If it is odd, then it contains only odd number of nitrogen atom. So that's the thing for nitrogen rule. So general fragmentation modes, you can see already we have discussed. I have given some idea. There may be simple cleavage which is homolytic, or it may be heterolytic. So when it will be homolytic cleavage, we'll get the neutral spaces containing single electrons. If it will be heterolytic cleavage, we'll get a cation and also anion. So if it is simple cleavage, the process involves homolytic or heterolytic. In homolytic cleavage, odd electron ions have an unpaired electron. Odd electron ions have an unpaired electron which is capable of new bond formation. When a bond is formed, energy released. The energy released by bond formation can help offset the energy required for the cleavage of some other bond in the ion. Homolytic cleavage reactions are very common and can be classed in the following types. If you take the model mode 1, this fragmentation mode operates in compounds which having heteroatom is slightly bonded to a carbon. So there will be homolytic cleavage. So R will be con- R will be removed as homolysis, and this charge, so we'll get double bond between X. The parent ion is formed by removal of one electron from the heteroatom, and a new bond is formed by adjacent atom through donation of unpaired electron and transfer of an electron from the adjacent bond. So R dot will be formed, and you will get this ion. So more abundant peaks are formed by cleavage of carbon-carbon bond, which is in the alpha position to the heteroatom in the mass spectra of alcohol, amine, ether, etc. So same way you will get the R dot, which will be removed, and with removal of R dot you will get the base peak of this one. So now you can see the mass spectra of three isomeric butyl alcohols are different, as you have asked the same question in case of neopentane. Here is given here. The mass spectra of three isomeric butyl alcohols are different. Secondary and tertiary alcohol or butanol. Secondary and tertiary butanol undergo this type of simple cleavage, whereas N-butanol undergo elimination to give peak at 56. Consider the cleavage of 2-butanol. So CH3, CH2, CHOH plus CH3. So CH3 dot will be removed. So we'll get CH3, CH2, CH double bond OH plus, having M by E ratio of 59. Whereas tertiary alcohol, when CH3 group will be removed, simply you will get CH3, C double bond OH plus and CH3 having M by ratio 59. But relative abundance will be different. In mode 2, when heteroatom is attached to the carbon by a double bond, alpha cleavage is preferred, is the preferred fragment mode. So R will be removed. Mode 3, benzylic cleavage is an energetically preferred fragment mode. It involves the cleavage of carbon-carbon bond, which is beta to the fragment. This one will be removed, and there will be rearrangement having the tropylium cation C7H7. Then heterolytic cleavage of chlorine, see heterolytic cleavage forming the cation. Retrodial reaction, diel reaction will also produce the cyclization, the reverse way, there will be decyclization. So reverse diels reaction. So we'll get the butadiene cation. Then hydrogen transfer, one hydrogen will transfer, you are getting the cation. So these are all different types of mode, the formation of fragmented ions or general fragmentation modes. and the important features of mass spectra of hydrocarbons. So you can see the figure here, dodecane spectra is given. So in case of dodecane, that means C12 H26. The relative height of parent peak decreases as the molecular mass increases in the homologous series. This already we have discussed. If you increase the molecular mass, the relative intensity or relative height of the parent peak, it will decrease. So here it is C12 dodecane C12 S26. So it will C12 means 144 plus 26, so 170 is the mother peak or parent peak. So the relative groups of peaks in the mass spectrum are observed 14 mass units apart. You can see here 29, then 43, 57, 71, 85. Okay, so C7 is like this. So all are having 14 mass units apart. The most abundant peak corresponds to CnS2n plus 1 plus ion. CnS2n plus 1. That means if you consider CnS2n plus 1, so C4H9 plus. The most intense peak are due to C3, C4 ions at ME 43 and 57 respectively. There is no preferred charge stabilization site to favor any specific cleavage. The peaks corresponding to CnH2n plus ion are also accompanied by CnH2n plus and CnH2n minus ion in the much less abundance you can see here. So all are having CnH2n plus 1 and CnH2n minus 1 peaks are also there. It is very important to note that relative abundance of the ions formed depends upon the stability of the ion forms and also stability of the radical which is lost. Now moving towards the branch chain alkanes, here is the branching. So bond cleavage takes place preferably at the site of branching. So that means either from here, here or here. Ethyl group or methyl groups will be removed. So you see the molecular formula is C9, C9S20. So C9S20 means 108, 128. 128 peak is not observed here. C9 is 20. So C9 9C means 108, 20, 128. Yes, 128 you are not observing. Highest peak is observing at 113. 113 means when we remove one methyl group, so 17 means move, so 113. So that's why the bond cleavage takes place preferably at the site of branching. Due to such cleavage, a more stable secondary or tertiary carbonium ion results. Here it is a tertiary carbonium ion. So we are getting that one. So largest substituent at a branch is eliminated readily as a radical. The radical achieves stability by delocalization of ion electrons. So the largest substituent, that is the ethyl group here, removes the relative abundance of the parent ion is least and is mostly not observed. Great number of fragments results from a branch chain compound compared to a straight chain compound. It is due to the greater pathway of cleavage. The signal corresponding to CnH2n plus 1 plus ions follow weak signal which appear 2 units below them. So here 3,3-dimethyl heptane, the figure is given here. So you can see here, as expected, the loss of tertiary free radical forms a peak due to C4H9. So a tertiary free radical, this will be released. Here you will get the C4H9 as the 57. You are getting that one. So that is the parent.
Sir, pardon, sir, here.
Also, the
So,
loss of NAS.
hello, sir. Pardon,
Hmm.
sir. Sir, so
Yes,
that
yes.
means the main for if through by observing this spectrum, if we want to pick that what is the actual molecule that could be, that means the right hand side always the highest mass that is only coming that way.
But in some cases, you will not get the mother twig. As in this case, you see, it is branched. So in this case, you are not getting the parent peak here. Molecular formula, if you consider it is 3,3-dimethyl heptane, so that means C9. So C9H, how much? 20. So C9H20 means what is the molecular mass? 128. You are not getting the 128 peak here. The maximum peak you are getting at 113. So because why we are not getting 128 peak here? Because whatever ion will be formed, the parent ion, that is a metastable ion. That is having least
Yes.
stability because it is a branched hydrocarbon. So when the cleavage will take place from here, where I am
Yes.
putting the cursor.
Yes,
So
sir.
what you will get a tertiary carbocation or a primary carbocation. That means you will get C4. This one, if cleavage will be here, you will get C4H. How much?
Nine. Nine.
9. And plus C4H9 plus, that is the cation.
Yes.
And
Yes.
this tertiary as the free radical.
C5.
One possibility. This tertiary carbocation, tertiary free radical, primary carbocation, tertiary free radical, or the tertiary carbocation and primary free radical. That means C5H11 plus or C4H9 plus. So these two, that's why you are getting the two peaks at 43 and 57 as the having nearly same intensity. So that indicates one fragment is 43, one fragment is 57, and out of these, one is a tertiary group, one may be primary. Like this, we have to rearrange. And total will be 113, that means one methyl group less. One methyl group less here. Because if you add, going on adding these two, 43 and 57, how much you are getting?
So 14. 14 different.
Hmm,
And
108.
CH2, methylene group different. CH2.
Mhm. See, in this case, if it is 57 means this one,
Yes, that's it.
C5. Hmm?
Yes, sir. Yes, sir. C5, H11.
Yeah, C5H11, that is 71. C5H11 is 71. And C4H9,
Yes, sir. C7.
that is 57. So 71 and 57, these two peaks, sorry, not 43. If you add these two, then how much are you getting? 128, but you are not getting the 128 peak here as I told previously. So the parent peak you are not observing here because it is highly branched. So as parent that will be a metastable peak. So you will not, as expected, the branch chain compound does not form any molecular ion. The most abundant peak, which is at that is 43, it is formed due to loss of most stable free radical. You can go through this one, this equation comes. How we are getting the peak at 43. This is the compound. Then here is the fragmentation. You are getting CS3, 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 CH2. Then there will be rearrangement producing this tertiary free radical. Then which will again after that one electron will be lost. So again rearrangement producing this peak at 43. So also small peaks are formed due to formation of alkynyl cation. So this is in case of branch chain alkanes. If you go for alkenes, or olefins, in this case, the some important features are the molecular ion peak in the spectra of unsaturated compound is more intense than the corresponding saturated analogs. The reason is the due to resonance stabilization. The relative abundance of molecular ion peak decreases with increase in molecular mass. The cyclic olefins also show group of peaks which are 14 mass units apart. Same thing. In general, mode of fragmentation induced by double bond is the allylic cleavage, and also there will be McLafferty rearrangement as shown here. So now we go for acetylenes or alkynes. For 1 butane or 2 butane, the molecular peak is the base peak. The relative abundance of molecular peaks decreases as the molecular mass of alkyne increases. Same thing what we are seeing. Now moving to cycloalkanes. Here the relative abundance of the molecular ion of cycloalkane is more as compared to the corresponding alkane. Cycloalkane relative abundance will be more. It favors cleavage at the bond connecting the ring to the rest of the molecule. Here, see, either cleavage will be here or here. Fragmentation of the ring is usually characterized by loss of two carbon atoms at the C2H4 or C2H5, 29 or 28 mass unit. That will be lost. So they differ by 28 or 29, not 14, as in case of alkane, alkene, or alkyne. The stability of fragment and depends upon size of the ring. Fragment ions are commonly observed by loss of alkene or alkynyl ions. The side chain of the ring breaks and the lone or odd electron remain in the ring. So now you see the N propyl cyclohexane is given here. The peak at 128, 26 as peak. So my other two unit. So M by E of 28, 128 is the molecular ion peak and is quite abundant. The largest peak, that is base peak, which occurs at 83, is formed by loss of the side chain. So 3 C3 H7 loss. So 43 C3H7. Yes, 43 unit loss. So get this one. The lone electron remains on the ring. The positive charge ion radical appears at 83. So that is the base peak. The ion radicals show retrodial Diels-Alder reaction, and the fragment is formed at what 55. This one, retro-Diels-Alder reaction. Then cycloalkenes or cycloalkynes. So here the unique mode of cleavage is the retro-Diels-Alder reaction. So it is an example of multi-centered fragmentation mode, which is characteristic of cyclic olefins. The fragmentation mode involves the cleavage of two bonds of a cyclic system, resulting in the formation of two stable unsaturated fragments in which two new bonds are formed. This does not involve any hydrogen transfer rearrangement. So we can consider this one, you can see retro-Diels-Alder reaction. So 6-member ring will cleave to a 4-member and 2-member compound. So the mass spectrum of cyclohexene, the peak at MA54, is found in fairly high abundance. So in the same way, you can go through the other examples are there, aromatic compounds. Some examples of are given for practice. Fragmentation of N-butane, fragmentation of 2-pentane, 2-pentene, sorry, fragmentation of benzene, how it occurs. Then moving towards the alcohols, different spectra, different fragmentation process. Okay, just 1 minute. So in case of alcohols, the molecular ion peak of primary and secondary alcohol is usually of low abundance, is not detected, and is not detected in tertiary alcohols. Tertiary alcohol will not get the primary molecular ion peak or the parent peak. The parent ion peak is formed by removal of one electron from the lone pair of the oxygen atom of primary and secondary alcohol. The number of fragment modes in alcohol depend upon the fact whether it is primary, secondary, or tertiary. The fragmentation of carbon-carbon bond adjacent to oxygen, that is alpha cleavage, is preferred as the preferred fragmentation mode. And generally, we will get signal which are differ by or which is at 31, which will appear as the large abundance in the mass spectrum of methanol and other aliphatic primary alcohols. And why this will get? We will get the that is due to CH2OH. So we will fragment here fragmentation, so CH2OH, so that we will get CH2OH plus. This is at 31. That is the base peak in case of most of the alcohols, primary alcohols, or any aliphatic primary alcohols. These signals correspond to the formation of the oxonium ion CH2OH plus. So now let us consider the spectrum of 2-butanol, which is a secondary alcohol. So in this case, you are getting the peaks at 45, 59, and 74. Having less abundance, so maximum is 74. So 74 is the mother peak, which is formed by removal of one electron lone pair over oxygen. So that's why the abundance is low. Already we have discussed. So then the various fragmentation, how it occurs, what other peak we are getting at 45, 59. Again, the difference is 13, but here is also same 13 or 15 here. So that means CH2 fragmentation occurs. So what are the different fragmentation processes given here? You can see. So CH3, CH2, CH, CH3OH plus parent ion. So which will decompose by CH3, CH2 free radical removal. So we'll get CH3, CH double bond. So 45 will get the base peak alpha cleavage, and at 59. So this part one methyl group will lost. So CH3, CH2, CH double bond OH. What? 59 and 45 and 59. We are getting two peaks. Okay. So like this others you can go through the about the phenols, thiols and thiophenols. All these things are there. Whatever book I have supplied or circulated, you can go through that one. This one same the IY Sharma. Now we'll move some particular examples and see how to solve. Unknown compounds are there. So let me take 5 minutes break. Then we'll discuss.
Sure, sir.
Okay, so let us discuss some problems. You can see the problem will come like this. An organic compound contains 66.6% carbon, 11.1% hydrogen. In UV, it gave a characteristic band at 275 nanometer with epsilon max 17. In infrared, it bands are formed at 2941 to 2857 medium, 1730, 1715 sharp, and 1460 centimeter inverse medium. In NMR, three signals appear at 7.5 to tau, a quartet of 2 proton, 7.88 singlet of 3 proton, and 8.93 tau value, a triplet of 3 proton. Determine the structural formula of the compound. Okay, so it is 66.6% carbon, 11.1% hydrogen, and rest oxygen, which is 22.3%. So from this value percentage composition, we can get the empirical formula of the compound, which was found to be C4H8O. Empirical formula is C4H8O, but not the molecular formula. Okay,
Yes, sir.
this must be the molecular formula. This must be the molecular formula. Since 8 hydrogen atoms are shown by NMR, you can see 2 proton quartet, 3 proton singlet, and 3 proton triplet. So total 8 protons, 8 hydrogens. But here in the formula also there are 8 hydrogens. So this is the molecular formula. At 275 nanometer, you are getting the peak in UV visible. So 275 represents the carbonyl group, which is due to n-pi state transition, the forwarding band. So that means the oxygen atom is present as a carbonyl group, and also that is uh, verified in IR spectra at 1715. The 1715 is due to the carbonyl group is also. The absorption at 2900 to 28, that is due to the CH stretching, as you know. 1715 is the characteristics of the ketonic group, carbonyl group, and 1460, that is due to the CH stretching. So we'll get the carbonyl. And in NMR spectrum, the three kinds of proton. So three kinds of proton means one is quartet, that means the neighboring should be CS3, then only we'll get a quartet, as in CS2, CS3, CS2. And the singlet is where we will get the singlet for this 3 proton singlet, I think. Yes, 3 proton singlet, that means the CS3 singlet. So structure will be CS3, CS2, CO, CS3. Okay, so like this you have to analyze the compound. Another say, let us see. No, we are not giving a complex structural check. Seven. A compound with molecular weight 116 gave the following spectral information: 283, sorry, nanometer, the peak. In IR, we are getting a peak, broad peak, 3000 to 2500 between, and 1715, a sharp peak, 1342, another wild peak. In MR, we are getting a 3 proton singlet, 2 proton triplet, 2 proton triplet, another 2 peaks, 2 proton triplet at 7.4, 2 proton triplet at 7.75, and 1 proton singlet at 1.1 tau. Find the structural formula of the compound. So 283, it indicates the carbonyl group. So there is a carbonyl group. So presence of carbonyl group is also further confirmed at peak 1715, and this broad band between 3000 to 2500, that is due to OH. We know OH stretching, and this is the most characteristics of carboxylic acid. Okay, which is due to hydrogen bonding, so it's coming like this. And the presence of acidic group, carboxylic group, is also shown in the NMR, which gives a singlet at the negative tau value minus 1.1. Thus, the compound, it may contain one carbonyl group, one carboxylic group. Further, the two triplets, which are at 7.4, two with two proton triplet, and another at 7.75, having the same integral area, two proton, two proton. It must be due to a CH2 CH2. So therefore, the formula will be CH3CO, CH2 CH2 COH. This is two triplet, and this is three proton singlet, and this carboxylic acid group and carbonyl group. So like this, you have to proceed, or other examples are there also, so you can go through it. Okay. So thank you. Stop
Thank
here
you.
today. Okay.
Thank you, sir.